It is a process in which there is no transfer of heat between the system and surroundings. If you are considering a system, the sum total of all the types of energy the system is having, the sum total of that is called as internal energy. How can you represent the change in internal energy? That will be delta U is equal to UB minus UA. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry, Vidhyaashram School of Excellence, Mysore. So today we are back with session 2 of the chapter Thermodynamics. So in last session, we discussed about what is thermodynamics, the introduction, right? And then we discussed about the different thermodynamics terms, yes, and then the different types of system, yes, and what is state function and path function and the various examples for it. And then we studied about extensive and intensive property, and then we studied about different thermodynamic process also, right? So in today's session, we are going to study about a state function, that is internal energy, and then we are going to study how you can bring a change in internal energy. So there are two ways in which you can bring a change in internal energy, that is by heat or by doing work. Okay, so in detail we'll be going to study about that, and then after that finally we'll be studying about the first law of thermodynamics. So as I said, the thermodynamics is governed by different thermodynamic laws. So we'll be beginning with the first law of thermodynamics today, right? So first topic, that is internal energy. Okay, so what is internal energy? As I said, it is a state function. Yes, what was the state function? Yes, it is only depending upon the initial state and the final state, and the path which is followed is not important, right? Only the initial and final stages of importance, right? So, it is a sum of all forms of energy the system can possess, right? Internal energy. If you are considering a system, the sum total of all the types of energy the system is having, the sum total of that is called as internal energy, right? It is the sum of all forms of energy. It's not like the system is having only one type of energy, right? Yes, it can have various forms of energy. So the sum of all these types of energies gives you the internal energy, right? So what you have to understand is, yes, the absolute value for internal energy cannot be determined. Yes, internal energy is represented by the symbol capital U, okay? Yes, and the absolute value for U cannot be determined. Always, what is it that you can determine? It is the change in internal energy. So how do you represent change in internal energy? Delta U. The delta stands for change, right? So how you can determine it then? If you can't measure the absolute value for U, that means for U, the internal energy, you can't calculate the U, but you can calculate the change in internal energy. Yes, if I'm saying finally the internal energy was U2, and initially the internal energy is U1. Yes, if you take U2 minus U1, you'll get delta U, that is change in internal energy. Right? Yes, so I hope that is clear. So how you can bring a change in internal energy, right? The change in internal energy, how does it happen? It can either happen by the passage of heat into or passage of heat out of the system. Yes, that means a heat is either supplied to the system or heat is being released by the system. In this case, yes, there will be a change in internal energy, right? If the system is losing energy, that means there will be a change in energies happening there, right? So that means, of course, there will be a change in internal energy, right? Yes. And the second way is by doing a work on the system, or the system is doing a work. Okay, so work done by the system or work done on the system. Either ways, yes, we can bring a change in internal energy. So yes, how the internal energy varies? Either by the heat passage into or out of the system and work done by or on the system, right? So as I said, it is a state function. Okay, internal energy is a state function. It depends only upon the final and initial state of it, right? So now we are going to discuss how we can change the internal energy of the system by doing work and by doing heat, right? So now we are going to see how we can change internal energy by doing a work on the system, Okay, yes. So now we are considering it as an adiabatic process. So in the last session we discussed what is adiabatic process. Yes, adiabatic process, such a process in which there is no heat change or heat transfer or heat acceptance to the system, right? It is a process in which there is no transfer of heat between the system and surroundings. Okay, so the symbol with which we represent heat is Q. Okay, it is Q. So that means adiabatic process, they will be having delta Q will be equal to 0, right? Yes, there is no change in heat there. Neither the system is transferring heat from the system to surrounding or the system is accepting any heat from surroundings to the system. So the change in heat will be 0, right? So such processes are called as adiabatic processes, right? So now we are going to consider a system. And the temperature of the system, that is initial state of the system, the temperature, let us say, or let us consider it as TA. So I have taken a system here. Okay, this is my system. And now initially, okay, before doing any work, initially the temperature of the system is TA, right? And the internal energy we are considering it as UA. Okay, so initially the temperature was TA and the internal energy was UA. Okay, right. And then we can change the state of the system by doing mechanical or electrical work. Okay, so now initially the temperature and internal energy was TA and UA. Now what I'm going to do is I'm going to do a work on the system. So this can be a mechanical work or an electrical work. Okay, so let's consider inside this tank there is water which is present. Okay, so either I can do mechanical or electrical work on it. Mechanical work means if I am inserting a rod there and I am continuously stirring it. So what is happening? A mechanical work is happening there. Right, I am doing the work. So it's a mechanical work. And another way is I can dip an electrical rod in it and supply an electrical energy there. That is, an electrical work can happen there. Yes, so either it can be a mechanical work or electrical work that can be done on the system. Right, so once the work is done on the system, now the temperature changes. Right, temperature changes to, let's consider TB. Okay, now if the temperature is changing, the internal energy also changes, right? Yes, it changes to UB. Let's consider it is changing into UB. So this is the setup. Okay, so now it is found that, yes, TB will be always greater than TA. Even if you are doing a mechanical work or even if you are doing an electrical work. Okay, it doesn't depend upon what type of work you are doing. Even if it is a mechanical or electrical work, yes, the TB is always greater than TA. That means the final temperature is always greater than the initial temperature. And hence how you can represent delta T, that is the change in temperature, that will be delta T will be equal to final minus initial temperature, right? TB minus TA, as TB is greater than TA. And hence how can you represent the change in internal energy? That will be delta U is equal to UB minus UA, right? UB will be the final internal energy and UA will be the initial internal energy. So if you take the difference, you get the change in internal energy. Right, okay, so I hope it is clear. Now, what you have to understand, as I said, a given amount of work done on the system, no matter how it was done. That means even if I am giving a mechanical work or I am doing an electrical work there, irrespective of the path, that is irrespective of what kind of work I am doing on it, yes, the produced same change of state as measured by the change in temperature of the system. Okay, so how delta T is changing, based on that the internal energy is also changing irrespective of what kind of work I have done. Okay, so hence what you can say, or sum total of this, what you can understand, it is not depending on the path which is followed, it is only depending on the initial and final state. So what you can say, hence internal energy will be a state function, right? Yes. Okay, so the adiabatic work done, that is the work done, and the subscript it is written AD for adiabatic. In the beginning I told you we are considering this process as adiabatic process. Yes, that means there is no transfer of heat between the system and surroundings, right? And required to bring about a change of state is equal to the difference between the value of U in one state and that in the other state. So how you can write, delta U will be U2 minus U1 which is equal to WAD. Okay, so we are doing a work here. Either it can be mechanical or electric work, but it is equal to the change in internal energy. That is delta U is equal to WAD. Okay, so your change in internal energy is equal to the work done in adiabatic conditions. Yes, so I hope it is clear. So what you have to understand here, the change in internal energy can be brought by a work done on the system. Okay, so now there is a sign convention that you have to understand, which is important for your numericals as well. Right, so if the work is done by the system, okay, the work can be done by the system or the work can be done on the system. So if the work is being done by the system, the sign convention, that is W, that is work, will be negative. That is the WAD value will be negative. If the work is done by the system, okay, if I am the system and if I am doing some work, that means I am losing my energy, right? So how you can say a negative value, right? Okay, so if the work is done by the system, the sign you have to use is negative. And if the work is done on the system, okay, that is if I am the system and if I am getting some energy, okay, I am having food and I am getting energy, that means I am positively getting charged, right? I am highly energetic now. So same way, now a work is done on the system means, yes, your work will be a positive value. Okay, so this is the sign convention, which is also important, right? So this was the first part, that is change in internal energy by doing a work on the system. Now the second one is change in internal energy of the system by heat. Okay, right. So the internal energy of a system can be changed by transfer of heat from the surroundings to the system or vice versa without the expenditure of work. Okay, so in this case, now what we are going to see is how the internal energy can be changed by the transfer of heat from the system to the surroundings, right? Okay, so in this case, we are not doing any work. It is only that heat is getting transferred, right? So in the first case, when we were studying about the change in internal energy by work, we discussed that it is happening in an adiabatic process, that is, there is no change in heat. Now, we are going to change the heat, but the work will be kept a constant, right? There is no work done. Okay, now this exchange of energy, which is a result of temperature difference, is called as heat. Okay, yes, and that is represented by the symbol Q. Okay, so heat is represented by the symbol Q. Now, in this condition, what we are going to take is water is taken at a temperature TA. Okay, so I have taken water inside this at a temperature TA. Initially, the temperature was TA, right? In a container having thermally conducting walls. Thermally conducting walls means that is the system can transfer heat between the system and the surroundings, right? Okay, thermally conducting. It can conduct heat now. Okay, now which is enclosed in a huge heat reservoir at temperature TB. Okay, now what I'm going to do is I'm going to keep this inside a reservoir. Okay, I'm going to keep this inside a reservoir which is having a temperature TB. Okay, so this system is having a temperature TA and the reservoir is having a temperature TB. Okay, so there is a temperature difference. So what happens? Yes, heat will get transferred between the system and the surrounding, that is the reservoir, right? Because there is a temperature difference, of course, right? Okay, the heat absorbed by the system, okay, heat is given by the symbol Q, right? So the heat absorbed by the system will be that temperature difference, how much it is there. So that will be equal to TB minus TA. Right? Yes, how much heat is being absorbed will be based on the difference in the temperature between the system and the reservoir that I have taken. I hope it is clear. Yes. So in this case, the internal energy will be equal to the Q, right? Hence, delta U will be equal to the Q, where when no work is done at constant volume. Okay? Yes, I hope it is clear. So, when there is a temperature difference between the system and the surrounding, yes, there will be a heat absorbed or released, right? So that will be equal to the internal energy. So how you can write? Delta U will be equal to the Q, right? That is the heat absorbed or released will be equal to the change in internal energy. Now here also you have to remember the sign conventions, right? So now let's consider the same case that we have discussed before. Now from the surroundings, the system is getting the heat. That means if I am considering myself as a system, okay, from the surroundings I am getting heat. From the surroundings, the heat is transferred to the system. Right, so that is a plus point for me, right? So that means your Q will be positive, right? And then from system to the surroundings, now the heat is being released from me to the surroundings. So that will be a negative value, okay? So I hope that is clear. So till now what did we study? A change in internal energy can be brought, or a change in internal energy takes place either by the, yes, transfer of heat or by work done. So together in general case, how we can write it? The change in internal energy will be equal to, yes, the heat which is being absorbed or released by the system, and it can be done by work also. So can I altogether write it like this? Delta U will be equal to Q plus W, okay, where Q is the heat and W is the work done. Okay, so this is about the internal energy and change in internal energy either by heat or by work. Okay, now coming on to the next one, that is very important, that is the first law of thermodynamics, or it can also be called as the law of conservation of energy. So you already know what is law of conservation of mass. So what it is? Mass can neither be created nor be destroyed, right? So same way, law of conservation of energy. What does that mean? Energy can neither be created nor be destroyed, okay? But can be transformed from one form to another, right? So the energy can get transformed from one form of it to another form, but it can't be created nor be destroyed, okay? We can convert electrical energy into mechanical energy. All those energies can be transformed between each other, but we can't create an energy or destroy an energy. Right. So also you can define it in this way. The energy of an isolated system will be constant. It is an isolated system. That means no change in heat or work or any changes is happening there. So can I say the energy of that system will be constant? Right. There is no transfer of any energies taking place because the system is isolated. So in that case, the energy of the isolated system will be constant. So both of these are the definitions for the first law of thermodynamics. Yes, what it is? Energy can neither be created nor be destroyed, but can be transformed from one form to another. So now let's see how you can mathematically represent the first law of thermodynamics. So initially, if I am taking the internal energy, we know that it's a state function, right? So initially, if I am taking the internal energy as U1, okay, associating that, how you can bring a change in internal energy either by heat or by work, right? So associating that, there will be a heat and there will be work. So this is the initial internal energy. So now I'm going to consider the final internal energy, that is U2. Now what is this U2? This U2 will be equal to the initial internal energy, whatever it is there, and plus the heat that is being transferred and the work that is being done, right? It will be the sum of all this, which will be the internal energy. That is a final internal energy. As I said, what is internal energy? It is a sum of all the energies which a system is possessing. So if I am talking about the final internal energy, that will be equal to the initial internal energy plus the heat and the work that is being supplied or released by the system, right? Okay. So if I'm taking this to this side, it becomes U2 minus U1 is equal to Q plus W, right? And what is U2 minus U1? The change in internal energy. How do you represent it? Delta U. Delta U will be equal to Q plus W, right? So this is the mathematical expression for the first law of thermodynamics, or it can be also called as law of conservation of energy. So I hope it is clear, right? So in the next session, we are going to discuss about work, okay? Work in detail, we are going to discuss about it, and the work done in isothermal reversible process, right? Work done in isothermal reversible process, and then we are going to study about two concepts, that is enthalpy and heat capacity, right? So I hope what and all we have discussed in this session is clear for you. So that's all for today. Thank you.